Okay. Um, so yeah, as I was saying about the last project, and maybe it's not the last project, since if I offer an extra credit project, um, that may give you something to do with your idle hours. I Yeah, I don't. I'm looking forward to more of those idle hours. It seems like no matter how much I do, I can't keep up. Plus, there are all these distractions. Like, what in the world is going on? Um, so how are you all doing? Glad to see everybody here. What did we say? We got Anthony, Caesar. Nice to see you. Coin, uh, Jason, Logan, Mario, Marcus in the house, Michael, Nick, and Samuel. Good to see you. Good to see everybody. Good showing. All right. So I'm going to unmanage participants and I guess put me as the. All right. So chapter 18 is so like I say the project is not quite completed. I've probably about halfway through articulating the questions, but more than halfway because I have a pretty good concept of what it's about. I just need to finish that off. So that should be later today and due 2 weeks from Wednesday, which will be I think the end, unless it's not the end. And for if people want extra time, I think there's going to be some leeway at the end, like a week or something, to finish things up. I'm going to need a week to finish things up, just to read. It's a fair amount of stuff that's amassed that I have not read. I stopped in the middle of the billiards project just because I had to keep up with new things. And there will be a midterm part 2 someday, over the rainbow. Which rainbow has a beard? It's been growing overnight. Okay, that's a reference to the rock band Cream and their Swablar lyric. The rainbow has a beard. How are we doing? Okay, so yeah, there were a few typos on midterm part 1. Okay, I'm glad to get some feedback about those. If you could enumerate those. I mean, it's kind of hard. I hope they weren't like fatal typos. Oh, question 1. Okay. I will check out question. Yeah, sometimes it takes me a while to get warmed up. So I should go back and review question 1 before posting anything. But I will keep that in mind as I read them and try to be forgiving of everybody with their foibles. Foibles, I think, is the French pronunciation. Foibles. No, I'm completely making that up too. All right, where am I? Oh, I'm over here. Okay, so let's move on to chapter 18, since this is probably going to take some time. There's just a lot of technical stuff in there about how to build complicated objects, right? And I'm not quite sure where we left off. So let's go to there. All right. So initializing, copying, copy constructors, copy assignments, copy terminology, moving. Yeah, move semantics. Okay. So I think we probably got through some of this initialization. I didn't think we have much time for this last time. So consider our vector as it was at the end of chapter 17, where we had what? It's a wrapper around an array, essentially, right? So here's your array, which is essentially just a pointer to the first element of the array. And then you know how many elements are in the array. And when you construct it, you use the keyword new to allocate memory for that array. And that allocates memory on the heap, or the free store as we like to call it. And this is not actually defined here, but we would like to also, besides allocating memory, initialize the data elements. I think we've seen that. And then a destructor. This is an explicit destructor. I think it's a good idea to include. Do you get a destructor for free? I think if you allocate memory on the heap, you have to write your own destructor, and you need to make it explicit. I don't know why. So a lot of times these square brackets are italicized. That's just a quirkiness of the PDF version. The real book doesn't have them like that. Okay. So what if we want to initialize a vector to a set of values that are not defaults? Okay, well, let's get our workbench set up here, because I haven't done that yet. So Visual Studio, and I think we're here. Okay. Oh, yeah, we had started working on the two bodies, so that's sitting on the. Let me get rid of that. Oh, actually, yeah, or the end body problem. Okay. So let me connect that to one of our code windows. So there's this one, but we want a different one, right? So how about this one? Yeah, which doesn't have its properties set properly. We need proper properties. So we're gonna go here, okay? And not sure why there's a gray zone in the middle there. Okay, we can. Is it the paint? Oh, it's the paint thing. Why is it just gray in the middle? It could be because the paint. Here's paint, right? Oh, okay. So let me close that other. I'm just gonna say get rid of that. Okay. So I'm drawing on this paint window, but I'm not seeing anything. Okay, so maybe I need to take this paint window and set its properties. What do we have? We have Start Menu, GIMP. And oh yeah, there it is with its scribbles and everything. Okay. Let's then get rid of the scribbles. No. I gotta be careful you got the focus in the right place. Alrighty, not sure what that window is either. So, yeah, that looks good. Okay, so we're all set up. What is this? This is, oh, it's chapter 17, right? Oh, I think we need to get the chapter. I should take some time to set things up first, right? So here's the, exclude that from the project. We're done with that. We're actually in 18. It says 17. I'm just going to continue on with my bad habits. Don't be like me. Make a new project. Give it the proper name. Maybe I should do that, but it's just going to take longer. So here we are in end bodies again. Can I just close that? Yeah. So I need to go to proper directory for getting source code, which programming code. So chapter 18 is what I want. I want to choose it by type, and I'm going to copy those files and put them into sorry, wrong place. Here, you can't see what I'm doing. I'm sorry. I'm just going to put them in here. It says replace. I'm going to skip this file. Okay, all the other ones. Okay, so maybe it was the standard library facilities or something. But okay, so those are all there now. And I can say Solution Explorer's source file. Well, no, right click here and say add existing item, and that's going to be chapter 18.2 section 1, which is including IO streams. So maybe they actually want to run something here. We've got our pointer to a double. We've got a copy constructor. Okay. So that's section 18.2, and it's just a prototype here. It takes a reference to a constant vector called arg, and presumably will copy its elements. And there's quite a few different ways to do that. I think there's actually an algorithm called copy, which takes iterators, little itty bitty iterators. Oh, they're like 4-byte iterators. I don't know, 32-bit iterators. And we have this is the constructor, and it's using the keyword new to allocate memory for S doubles, S being the size that's being assigned here by the constructor. And notice that syntax might strike you as a little odd. I would note that these can be curly braces. This is the initialization list, right? And so a lem, which is the pointer to a double, takes an initializer, and the initializer allocates memory for S doubles on the heap, and passes to a lem, assigns to a lem the address of the first of those, right? Vector constructor here, this is the copy constructor. Oh, and it says so over here, right? So define copy. So we're going to need to define the copy constructor here, I think. Well, we'll see. Then we have the destructor. Some getters here, and a setter for setting the nth element of the vector to the value v. V is a little badly named. If it's a double, call it D, not V. V sounds like vector. Yeah, all right. So, and they're saying, you might want to add more stuff here, but what have we got for the copy? Okay, I think this is a little bit different than what's in the book. Let's see if it is. I'm going to put this on a separate line just because make it more readable, right? So basically it's just using a standard for loop to do the copy. Could we use a range-based for loop? No, because of an array doesn't know how big it is. So you really have to have this size parameter here to say how big it is. All right. Arg is the element being passed in. We're just accessing its ith element through the lem pointer, and the subscript. Where is it? Yeah, and the subscript operator. So the ith element of a lem which is actually the I plus first element of a lem, of arg. Arg's a lem array is assigned to the caller's a lem array, right? The caller being whatever vector object is calling is using this copy thing, right? And then so yeah, right. So copy is defined here, and then the copy constructor just calls copy. Well, I mean, it has the usual initialization list, but then it's going to copy whatever is in the parentheses here. Okay, so we have a vector v with 3 elements. Yeah, so this is the size thing, right? So that's, which constructor is that? That's this constructor, right? It takes an integer s, and that's 3 here. So do we have initialization? Where's this? Yeah, so this is the full definition here, right? So it's not initializing. Shall we initialize? How would you do that? Well, you would say for int I equals 0, I less than size, increment I, and set a lem of I equal to whatever you want the default value to be, probably 0, right? And so now these will all be zeros, right? As before they would have been garbage values. I think I kind of remember seeing that. So here's the assignment operator being used to copy. Have we overloaded the assignment operator? I don't see that anywhere here. That's one we tend to get for free. So maybe let's go back and read a little bit in the text to see, you know, what's leading up to here. So yeah, what if you want to do something like this, right? You want to create a vector from a list. Right, that would be much better than this tedious and error-prone method. So, yeah, and this is also tedious and repetitive. Plus, we don't have a pushback function, do we? How do we write a constructor that accepts an initializer as its argument? So a curly brace delimited list of elements of type T is presented to the programmer as an object of the standard library type initializer list. Oh, well, there's a standard library type initializer list. Let's see about that. So we go to our friendly neighborhood browser, and about here, I think C++. I think once we've got the zoom thing going, we're not in danger of losing that just by writing over. No. Okay, so CPP reference has a little something on that. Not to be confused with member initializer list. Uh-oh. Oh yeah, right. That's that little thing in the zone between the parameter list and the body of the function, right? The constructor. It's a lightweight proxy object that provides access to an array of objects of type constant T. All right. Automatically constructed when a braced init list is used to list initialize an object. Well, in the standard template library, which is, you know, we don't have that. We're trying to see how is that built. It's got these iterators, and it's got some non-member functions. R begin. What is the R for again? Um, reference maybe? Should we look up R begin? Oh, reverse. Sorry, yeah, reverse. Um, and so here's some examples of how that's used. But let's go back to our code. Our text. And let's see, how is he doing the initializer list here? Okay, so here's his constructor. Yeah, I'm a little worried about this. Okay, so, and we wrote this little bit of initializer here, right? But we don't have this. Oh, right, so, yeah, compare this. I'm going to copy this to the clipboard and go over to our code and use that to compare the... Okay, I think we just don't have this yet, right? Where shall I put it? Oh, so here we have a constructor that just takes the size and defaults to zeros. Here we have the copy constructor, and here we have one with an initializer list. So where does that initializer list live? Do we always just have access to it, or what's Stroustrup telling us about that? Standard temp library type. So let's go back to the browser and see if it tells us where does this thing live. Initializer list, right? So we're going to have to include that. All right. Go back to our code. Now what happens if we go down here? Still nothing, right? So what is the, what do we learn about? Yeah, I was a little worried about this. Lightweight proxy object provides a standard initialization list is automatically constructed under those circumstances, may be implemented as pairs of pointers. The underlying array is not guaranteed to exist after the lifetime of the original initializer list object has ended. That sounds worrisome. And they have this example here. And it looks like it's necessarily a template object, right? Which we don't have a template object yet. Well, I mean, it's one of the things we want to do today is build templates into our system. But, okay, so well, they're prefixing it with a stud. I don't know. Do we need to do that? I mean, we are. Let's see. We're using. Oh, we're just using that one standard cout. So maybe if I do that, yeah, that seems to make it happen, huh? Okay, so we're going to take an initializer list of doubles, right? And this is a template object, but we're specifying what things it takes, and we're going to take the size of the list that's passed in and assign to double. Does that work? Oh, well, look. So we have this sort of list thing, right? Oh, all right. So, so this list thing is, well, yeah. So this is we're attempting to copy this, but do they do that in our example here? Or I don't see a copy. Maybe I need to search for a copy in particular. So if I go back and say, yeah, I want to search for copy constructor. Beware of copies with standard initializer list. Yeah, I was a little worried, like I said. Not sure. So this is Tristan Brindle. of TristanBrindle.com, no less. Never heard of him. But he's including memory, string, and vector. He's using a unique pointer. Pop quiz. What does the following C++ program do? So we're taking the unique pointer template of a string, blah, 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 which is a vector. And this is a trick question, of course. The answer is that the above program will fail to compile. If this surprises you, then you're not alone. When I first wrote something like the above, I expected it to work just fine. If you want to know why this fails and how we can work around it, read on. Okay, so it's using unique pointers, which unique pointers is a way of not losing. What's a dangling pointer? Have we talked about that? Maybe that deserves its whole thing here. So, what's a dangling pointer? I think maybe we should specify our language. Geeks for Geeks has something on it. Stack Overflow. Maybe I'll go with them first. I know this is a pretty common question, but still new for me. I don't understand the concept of dangling pointer. Was Googling around and writing test methods to find one. I just wonder, is this a dangling pointer? Okay, so we've got a function that takes a string called name, constant string. It has a, so new foo will do something, but it's taking in a pointer to a character, right? Which is essentially a C string. So you're taking this stud string called name, converting it to a C string as you pass it to this function that takes a pointer to a constant character or a literal string, or a C string, I guess. No, that's not a dangling pointer. A dangling pointer is a pointer that points to invalid data or to data which is not valid anymore. So unique pointer can't be transferred to another place. Maybe we should wait to read about that in Stroustrup. But in any case, where are we? Oh, we're not in a tree. Is it here? Yeah. No, that's not it either. I've got a lot of stuff going on here. Yeah, as usual, right? How are we doing? So I kind of lost where my search was. Yeah, it's not that. It's not this guy. It's what is a dangling pointer? So maybe I just overwrote what we were reading before with this. I think I must have, huh? No, don't see it. All right. Sorry, we were looking at the initialization list, and so maybe I'll just look for that. So initialization list, C++, and copy constructor. Okay. Stack Overflow has something on this. So there's an example. So this guy's not including any fancy libraries. Maybe that's not a good one then. So list initialization. So initializing an object from a brace to knit list, right? That's what we want to do. Okay, so here's an explanation. The effects of the list initialization on object of type T T is an aggregate class and the initializer list has a single element of the same or derived type, possibly CV qualified, which is a comma separated value. The object is initialized from the element by copy initialization for a copy list initialization, or by direct initialization for direct list initialization. Alright, that's pretty arcane. So there's various narrowing. So here's, an example, but okay, so in this example, they got map and they've got vector. Alright, well, let's go back to our code. I'm sorry, that was a little bit of a dry sidebar, but for summary, what does it say here? Initializer list constructor. No suitable constructor exists to convert from constant double to vector. Yeah. So presumably the vector is taking an initializer list somehow. How does it get into the parameter list? So I mean, this part is the same, but this part, and so he's referencing the appendix, appendix B, section 5.2, which I suppose we could go there, but this is not going to work, right? So maybe we should just leave it at that. Let's go back and read, why is he telling us about this thing that doesn't work? So we use the standard library copy algorithm. It copies a sequence of elements specified by its first two arguments, beginning and end, to a sequence of elements starting with the third argument. Here the vector's elements starting at lem, right? So you see that's the third argument of this. Is that what's actually, yeah, that's in the code here. But it don't work. So he says now we could do this, right? And is that in main for our example here? No. So if we try to compile this, it's going to choke on that copy constructor, right? Right here, right? And the error message is conversion from size underscore t to int requires a narrowing conversion. And then function does not take 3 arguments? Really? Huh. So you think I can just get rid of the third argument? Should we go to that section in the appendix? Yeah, I've had the weird feeling that I've been here before. Okay, so we are on page section 18.2, all right? And we're going to go to the appendix B, B5.2. Oh, sorry, we should be looking at the text. The modifying algorithms, also called mutating sequence algorithms, can find and often do modifying the elements of their argument sequences. So I don't see initialization list in this group, so I do see some utility algorithms in 5.3 with uninitialized copy, initialized fill, but I don't know. Can I just search for it? Let me go up here a little ways and say find initializer underscore list. Oh, B.6.4. Yeah, this is one of those places in the text where they didn't quite iron out the wrinkles. All right, so what have we got here? Initializer list. We find the definition of initializer list here. It takes an initializer list. So there's a variable of type initializer list called no except. It has a size t, constant no except, number of elements, the first elements and one past. She's an initializer list with elements of type X. The list is used to construct an initializer list. Unfortunately, initializer list does not support the subscript operator. Well, is there another reference to that here somewhere? Can I say F3 and find the next one? Yeah. And then we're back to 18.2. I don't know. Do we care about this thing? So there's the initializer list. And the copy, which takes 3 arguments here. Sorry, need to get back to the code. Takes 3 arguments here, and yet what we're finding is that that's not always the case. So I'm going to go back. Is this where we were looking before? So this is okay, so inheriting constructors, initialization order. Yeah, that's not list initialization. Yeah, sorry folks. This is not great. Looks like a sort of an oddly, should we say initializer list? Maybe I'm using the wrong search terms here. So how about with an underscore as well? And oh, yeah. Okay, beware, there's that guy. Okay, so list initialization. Copy constructors gets called instead of initializer list. This is in stack. So this code here. So here they've got initializer list, and then I don't see a copy. We may just have to bump on past this because it's not working out, huh? Okay. What if we were to get rid of that third thing? I mean, how would you know where to copy it to? So how about if I were to sort of say, yeah, copy, of course, it just takes 2 parameters. No, she doesn't like those parameters. Too many arguments in function cell. Maybe it just takes 1. How about that? No suitable constructor. Yeah. Well, you can see what the intent of it was, but it just doesn't work like that. Shall we throw this fish back in the sea? Let's take it to the dumpster. All right. Ooh, it's a smelly dumpster. Okay, so I'm going to add existing item 18.2.2. Does this also have this funky copy function in here? All right, so this has some other stuff. So here we got our private data elements, the copy. Yeah? Oh, you can't see that. Sorry. Right, so I've opened up 18.2.2, the source code, and we see that we've got these 3 private elements here. So if we go back to the text, let's see if we can catch up to that place in the text. So I don't know. Initialization was a dumpster fire. I don't know. Should we try to recover some burnt embers from in there? Yeah. The copy is a sequence defined by the first 2 arguments here, beginning and end of the initializer list, to a sequence of elements starting with the 3rd argument. Seems obvious enough. I mean, I'm sure I've done this. So there's a couple of examples. Note how the use of parentheses for an element and the use of curly braces for element lists. We need a notation to distinguish them, right? So this is 1 element with the value 3.0, and this is 3 elements with the value 0.0. This is not very elegant, but it is effective. If there is a choice, the compiler will interpret a value in curly braces list as an element value and pass it to the initializer list constructor as an element of an initializer list. If you say so, Bjarne. In most cases, including all cases we will encounter in this book, the assignment operator before an initializer list is optional. So you can just skip the assignment operator there. It's a matter of style. If you think the assignment operator gives more clarity, go with it. All right, so we're into copying in 18.3, and okay, so this is not quite the code on our workbench because we were going to have a copy constructor as a private member function. Okay, I think we're going to develop that here. I don't see it yet, huh? Not yet. Huh. Okay, well, back to where we were. Yeah, nothing new there. So we're going to try to copy one of these vectors. Oh, okay, that's what that last bit of code was doing. So what happens here when we assign one vector? So we create a vector with 3 elements, all zeros right here. And is this... I'm sorry, I'm sneaking ahead here to look at... I think maybe this is... Okay, so I'm going to bring back that last one. All right, so I'm back into the code here. And let me just add in rather than deleting anything. So I'm going to add an existing item, 18.2.2, oh, 0.1, I guess. Okay. Here, can we just comment this thing out? Okay. And then we see that, yeah, what happens when we try to assign one vector to another vector? And that's kind of what Stroustrup is asking here, right? What happens when we do this? And I think that's pretty much what we've got going on here. We create a vector with 3 elements. They actually have a little bit of code in here. Let me bring that to bear. So yeah, we're creating a vector with 3 elements, all zeros presumably. Do we have the initializer up here? I don't know, I keep forgetting what's what. Yeah, all right, so our initializer, yeah, we wrote that little bit of 0.0 assignment there. So now in main, creating a vector with 3 zeros. We're going to assign that to v2. But first, let's set some of the values, right? So v dot set. Yeah, we got a function called set, and it says which one do you want to set. So I want to set the 3rd one to 2.2, let's say. And what happens when I copy v to v2? Well, ideally, v2 becomes a copy of v. That is, the assignment operator makes copies, right? So the sizes are the same. So, I mean, we haven't overloaded the assignment operator to work here. If we go back up here, we see there's no overloading in our class definition of the assignment operator, right? But it's one of those operators you get for free if it's obvious what the default behavior should be. And so we want the size to be copied and all the elements to be copied, right? All memory is returned to the free store upon exit from our function. Oh, this is one with a function. Yeah, there's quite a bit of changing from. Yeah, but if we were to exit main here, sorry, we would free this up, right? That's what the standard library vector does, but it's not what happens for our still far too simple vector. Our task is to improve our vector and to get it to handle such examples correctly. But first, let's figure out what our current version actually does. Exactly what does it do wrong and how and why. Once we know that, we can probably fix the problems. Okay, well, let's see. Let's print out what they are, right? So I'm going to say see out here the values of v are I don't know, can I do we have a getter? Yeah. I think I can just say 0. V dot get 1. Oops. And it's a little awkward here. V dot get 2, right? And let's say then also what the values of the other one are. The values of v2 and I'm not even sure this is going to compile, but we commented out that bad copy code, so it should, right? No, I've got link. Oh, it's because I've got several different things open. So let's put this fish back into the dumpster pile and try that again. Okay, so we're getting an output window, and let me put in some new line stuff here because it's a little hard to read. Okay, that should be all right then. Oh, it doesn't like the end line. Okay, so here's my output now, and yeah, well, that seemed to work all. Oh, I see. Those other outputs are from later on. Okay, so yeah, I made a pretty good copy just using the assignment operator, right? And we didn't even overload it, right? Just that's what we get for free. Could we also, does it also copy the size one? So yeah, so for that, sorry, I should have done this in the first place. Let's say for int I equals 0, I less than v dot size, right? Because that's a getter function for the size. We're going to see out all right, well, That was entirely too much trouble. Can we do it for the other one as well? Same kind of thing. So this is going to be V2. Right. So the test being, does it actually get the size as well from the copy, right? So, and sure enough, there you are, right? We now have a trailing comma, right? But that's okay. So okay, so the default meaning for copying for a class is to copy all the data members, right? So you're copying one object of type vector to another object of type vector, whether it's data members, public or private, and just copy them all from one to the other. So when we copy V to V2, they actually point to the same area in memory. So V2 doesn't have a copy, it has the actual same thing, right? So it's actually looking at the same memory location, right? Because we actually copied LM as well, right? Is that what we want to do? So they say, what if in between the copy you were to do something like this? So right, so we copied, and then we want to change V, say the third element to some ridiculously large number. Sorry, that's the wrong syntax, right? Yeah. So now, so you wouldn't expect that. So we've already copied V to V2, so you wouldn't expect V2 to change, right? Whoop, I now have a, oh, that was a, what am I doing? Okay, but look at the output, right? Oh. All right. I expected them both, since if they were both pointing to the same memory, then they would both have changed. But V2 still has the old version. Okay, so how is he pulling this off here? Let's go to the code and look at this copy constructor. So here the copy is in the private section. This is not the case here, right? I mean, in this 18.3, which is where we were reading in the text, they don't have this line here. They don't have a copy constructor at all, right? So let's take that out. And what else don't they have? They don't have that, which is defined down here. Okay, so this must be what's actually creating new memory. Okay, so let's get rid of that as well. And this is the copy constructor. So this is, okay. So without those things, if I try to do this, what happens? All right, so is it going to compile now? No. Why not? Unresolved external. Oh no, not that. Anything but that. So that means that I have a bad function definition somewhere. Oh, I think it must be that one, huh? Yeah, that's a copy constructor. Okay. Yeah. All right. So this is, here's the output now. So you see that I first copied V to V2 while V had the value 2.2, and then I changed the value of V, expecting it not to change the value of V2 because V2 was a copy, not the same actual object. But in fact, the way this is set up, it's the same actual object, right? And plus I'm getting an exception thrown somewhere in here. All right. Yeah, you can see it's gone to assembly code, and it's triggered a breakpoint that int 3. I'm not sure what's going on there, but yeah. So let's stop running this code and see. Okay, so what did we do? Well, well, maybe let's go to the text so we can see what he says to do, right? So right here we've got a problem. If we don't write our copy constructor correctly, then the copy is actually just it's just an alias for the same object, the same memory location. So whatever happens to one happens to the other, whether you want it or not. So if you were to write V set the second element to 99 and V2 set the first element to 88, and then print out V's first element, then V's first element is going to be 88, right? Because we're actually dealing with the same memory. And actually, I think we saw that in the output, right? That second line. So that's not what we wanted. Had there been no hidden connection between V and V2, we would have gotten the output 0, 0, because we never wrote to V0 or to V1, V2 of 1, right? You could argue that the behavior is interesting. Oh, that's neat. Or that could be useful. But this is not what we intended or what the standard library vector provides. Also, what happens when we return from a function that does that is an unmitigated disaster. The destructors for V and V2 are implicitly called. V's destructor frees the storage used elements, leaving that, and so does V2's. And so you're going to be deleting the same memory twice, and we've seen that that's a real problem. So we developed these things called copy constructors. And so we're into section 3.1. What do we do? Well, we'll do the obvious. Provide a copy operation that copies the elements and makes sure that this copy operation gets called when we initialize one vector with another. So initialization of objects of a class is done by the constructor, so we need a constructor that copies. Unsurprisingly, this is called the copy constructor. It is defined to take as its argument a reference to the object from which to copy. So for the class vector, we need a copy constructor that looks like this, and I think we have that here. I'm just going to uncomment this, right? So there's our copy constructor, yeah. This constructor will be called when we try to initialize one vector with another. We pass by reference, right? That's this little ampersand here. Because we obviously don't want to copy the argument of the constructor that defines the copying. We pass by const reference because we don't want to modify our argument. So we refine the vector like this. So we now have, yeah, and this is in the public section, okay. The copy constructor sets the number of elements and allocates the memory. Okay, so where is this thing defined? Down here. And let me just copy this code and see if this isn't the same. This may be different, so let's take a look. So this is the definition for the copy constructor, and in our code, yeah, it's this here, right? And it looks to be not quite the same, because we're using the initialization list. Oh, and then we're using this copy function. Right. So this was causing. Yeah. So this is what's in the text. And this is causing problems. If I hover over the IntelliSense here, it says copy elements. Yeah, it actually looks like it wants us to do it this other way, and it's actually got the exact. You can't see it, but if I hover over that, it says, yeah, you should do it like this up here. All right, so I'm going to comment this out. And use what was initially in here, right? Which is just doing element by element copy. A little for list. I'm not sure why. Is that a private data member or something? Is inaccessible. Yeah. It is inaccessible. So we have to get that through the size function. All right. And these are also private data elements, right? But we're in the scope of the vector class. Oh, but yeah, so this guy is accessible, although it says here that it's undefined. But this should be our getter, right? So can I just not? Can I just? Well, it's not. Let's just say get I. What's the problem? Object. Oh, qualifiers, right? So our getter needs to have a constant modifier here, right? We're not going to change the thing, so let's just make it constant. It's funny because it was working before, right? It's qualifiers that are not compatible. Oh, okay, we just got rid of that error, right? So what's this error here? And why is this underscored here? Has no member function copy. Oh. Yeah. What do we do with it? Oh, right here, huh? Okay. So, yeah, now it's happy. Oh, yeah, and that's happy too. Okay, so we just needed to uncomment that. Rough sledding here, sorry. All right, so does it work now? I don't know. I don't see any IntelliSense tingling. Did I make it work again? I still have unresolved external. Referenced in function main line 1. Something it doesn't like here. So we got rid of this initializer list. but the rest of it is okay. And we got our nice, oh, here, yeah, so do we need this? Yeah. All right, so we're back to working. Jeez. Here's the output. So as you can see, as you may recall, we assigned 2.2 to V2, to V, and then we copied V to V2, and then we changed V's third element to some large number, which didn't change V2's third element, right? So they're actually doing what's called deep copy, which creates actually a new block of memory. And so where's that happening? So this definition will initialize V2 by a call to vector's copy constructor with V as its argument. Again, given a vector with 3 elements, we get this, but now they're pointing to different memory locations, right? And when we call the destructor, it'll do the right thing. Each set of elements is correctly freed, and the 2 vectors are now independent so that we can change the value of an element in V without affecting V2 and vice versa. So now we get those 0, 0 values. Great. And we could have, instead of doing it like this, we could, should we check that that's true? We've been chastened to not necessarily believe what it says. All right, so this is, instead of using the assignment operator, I'm just saying construct V2 from V. And again, we never overloaded the constructor, the assignment operator, right? That's working fine. Okay, good. Phew. All right. So, but the copy constructor, works. So the assignment operator works like the copy constructor. So those are interchangeable, right? So if we define a copy constructor, which we are doing here, right? We're saying if you're going to copy this argument here, then you can do an initialization list to copy, to allocate memory on the heap for and this is new memory now, right? So this is allocating new memory on the heap, and it's saying copy arg, which is this, and then copy is this function here, right? Which is doing an element by element assignment. Do you suppose I could have? See, before I used the getter function, but I think maybe you don't need that. It was just, yeah, see? I could, so you might say, well, arg is being passed in as a reference variable, a constant reference, and so I shouldn't have access to its private data elements. I only have access to the caller's private data elements. So this is accessible, but this is not? Well, no, actually, they're both accessible, right? Because we're in the scope of the vector class. We can access its private elements even for one passed in as an argument. All right, so that's still going to work. Should we double check that? Yeah. So I didn't have to use the getter. It was only because I hadn't defined the actual function. All right. Moving on. So 18.3.2. Sorry, maybe we should read this last little paragraph. When V, the initializer, and V2, the variable being copied, are of the same type and that type has copying conventionally defined. These two notations mean exactly the same thing, and you can use one, whichever one you like better again. Okay, great. So copy assignments. We handle copy construction initialization, but we can also copy vectors by assignment. Wasn't that what we just did? Yeah. Oh, so here he's actually going to overload the assignment operator. See it there? Yeah. Huh, it's funny because that did work, right? That's just exactly what we did in... Oh, yeah, we did the equal assign operator. Monkey see, monkey do. So we handle copy construction initialization, but we can also copy vectors by assignment. As with copy initialization, the default meaning of copy assignment is member-wise copy. So with the vector as defined so far, assignment will cause a double deletion exactly as shown for the copy constructor, plus a memory leak. Okay, so that sounds bad. So let's put this. I think, can we get something close to this and put it on the workbench? So I'm going to get rid of this, I guess, and bring in. I think, is it 18 just 2? Let's take a look at what this is. So yeah, it's got this section here under the private member function, which I'm not sure if that's what we want. And then we got F2, which yeah, is doing essentially what F2 is doing in the text there. Yeah. So, all right, so in main, we create a vector with 10 zeros. Oh, well, I'm not sure. You know, you always have to double check on how the constructors work. So here, it doesn't have it again, right? So these won't, well, let's run this thing and see what it does. Okay, it does nothing. Here's the output. So maybe we should have it do so. So this is just self-assignment. Oh, what would happen if you assign something to itself? But let's check here. Okay, so I'm going to say for entire cosine I less than v dot size increment I, and see out v dot get I followed by a space. Oh, I don't think we're including any libraries here, huh? Yeah, which makes you think, well, this is just for theory. But let's go ahead and see if we can make something work here. IO stream. And alright, so now, yeah, okay. I'm going to try to run that. Right, and we see garbage, right? As well we might expect. So how do you fix that? Well, you know, do your initialization in the constructor here, right? So I'm going to say for int I equals 0. Do a lot of this sort of thing, huh? I less than size increment I, and say lm of I is 0.0. Okay, so now if we run this thing, we get all zeros. Okay, 10 zeros, as the case may be. Oh, we're running up on a break, huh? So, I don't know. What do we got? 7 sections. So we're almost halfway through 18. Although, um, yeah. All right. So, uh, what's the point here? Uh, so if we had this code and we overload the assignment operator, are we overloading these? I don't see the. Oh yes, sure enough. Okay. So is this the same overloaded assignment operator? It looks like it is. Yes, exactly the same. So maybe we can take a look at it in the code then. So the assignment operator is going to take a reference to a constant vector A and allocate memory on the heap for size doubles. So this is new memory, right? And then we're going to call copy on A, and then we're going to delete the old memory, assign the address of the first of the new memory to our lem, assign size to size, a dot size to size, right? That's because we're going to have the same, and then return it dereferenced this, right? Which is going to be, I don't know, why is there an ampersand here? Let's read and find out. Okay. So we would like v2 to be a copy of v. That's what the standard vector does. But since we have said nothing about the meaning of assignment of our vector, the default assignment is used. That is the assignment that is member-wise copy, so that v2's size and lem become identical. So we're just basically have an alias, another name for the same object, the same memory chunk. We don't want that, right? So when we leave F2, we have the same disaster as we had before, deleting doubly. So it's the same thing, right? We define the we define the assignment that copies properly. Okay, and we just talked through that. We were kind of wondering about that ampersand. It's yeah. So assignment is a bit more complicated than construction because we must deal with the old elements, right? So it's this deleting of the old elements. Here. Basic strategy is to make the copy of the elements from the source of the vector, from the source vector. So here he's using this copy thing again, which I don't think we're doing that, are we? No. So he's got this copy function, and I don't see that in our code. Then we free the old elements, and finally we let a lem point to the new elements, and this now looks like this. All right. So v2 was pointing to a new copy, which then we free up, and first we free that up, and then we assign this to what the new memory is. Now the vector doesn't look doesn't leak memory and doesn't free any memory twice. When implementing the assignment, you could consider simplifying the code by freeing the memory for the old elements before creating the copy, but it is usually a good idea not to throw away information before you know you can replace it. Also, if you did that, strange things would happen if you signed a vector to itself. Yeah, as it is, we're doing that here, and it's not a problem, right? So we check that. So in main, we do self-assignment, and there's no problem. And maybe we should try printing it out again, right? Oh. Well, looky there. So we make a copy of the vector onto itself, and then it gets, all the initialization gets lost. Go figure, huh? So why is that? Well, what does the copy? What does the assignment operator do? Well, let's review it here, right? Is it really doing what we said it would do here? Okay, so we're copying V to itself. All right. So we allocate memory for as much memory as V has. This would be, V dot size here to the heap, and assign the address of the first of those to P, which is a pointer to a double. Then we call copy on V, right? And that so P is now pointing to a new chunk of memory, right? Which is uninitialized. Then we call copy on V, and copy, well, where's the copy here, right? We'll assign the elements of V's to the new one. All right, so these were all zeros, right? And then we delete the old one, and now reset P to point to this new, or lem to point to where P is, which is the new chunk of memory, which still hasn't been written, right? So we copied, yeah, actually it should have been written right there, right? We pass it in by reference, but a constant reference. But this is the new memory, right? And it's copying the old memory. Oh dear. Yeah, that's a little confusing, isn't it? So so here's copy. Should we do something else in here? I could say, yeah, we're going to do this, and then we're going to say cout a lem of I equals a lem of I. And those should be zeros, right? Should put a little space here. Okay, I'm looking at the output here, and I should share that with everybody. And we see, yeah, lemma 0, 0, lemma 1 is 0. All those things are zeros. And yet when we go to print out the new v, we get garbage values. So copy is called right here, right? So we're saying copy A to the left side of this operator is the lem that's the calling lem, right? And so that should be these values, right? So we should be setting yeah, so we copy v to itself, we destroy it, which doesn't make a lot of sense, does it? So this is so there's a different copy here. Let me show you what's in the book here, which is to copy a.lem, which is an iterator, right? This is the one that doesn't seem a.lem plus a.size, right? So that's going to be the end iterator. And this is going to be a lem. And it does not like that. This is maybe it's because it's constant. It's like, okay, you know, if you're accessing these memory locations and you're not sure you're not going to change them, then it's going to throw it. What's the memory? What's the no suitable constructor exists to convert from const to double pointer to constant double to vector. Yeah, it seems to think that copy only acts on right, but this copy up here is what copy? Is it? Oh, sorry, let me get to the Stroustrup. It's a bit of a mess in here, huh? Yeah, see, here's do we have another copy up here? Yeah, see, this copy here is doing that same thing, right? And so is this one. Oh, yeah. So that's just referring to this actual code here. And that's actually not okay, right? It doesn't like that at all. And it seems to be because it's constant. So what copy is this? Can I like go to definition? So if we go to definition, that's down here, right? Okay, so it thinks it's this copy. And which copy is that? Is this the one where we actually rewrote it, right? Because right, but that was in the previous version. Oh, this is going to drive me nuts. Okay. Where was that copy constructor? I mean, yeah, that copy function. 18.2. I'd like to make that work. That's initialization, copying. All right, well, we're going to have to take a break here. Yeah. And they're referring to this function in appendix B.6.4, not 5.2. And it looks like things changed midstream here, and they never really coped with how that was changing. So we do have this problem. So I don't know. Let's put a bookmark there. Problem spot, and we'll move on to copy terminology, which is here. And then let's do that before the break. So can we? Yeah, we don't have much time, huh? So let's just say that shallow copy versus deep copy, right? So shallow copy is just an alias. It's the same object in memory. Deep copy, you actually allocate new memory and copy those, so you have two versions of the thing, right? And they just give some examples of that. So we'll talk about moving after a short break, because I think this concept just requires some fresh eyeballs. All right, so any questions before we take a short break? Okay, I'm going to pause the recording. And so, move semantics. Now this is kind of like a magic trick. I can only imagine when the discoverers of this stumbled upon it. It must have been one of those moments. It's like, holy cow, you can do this? All right, so maybe we should search a little bit on this, right? So where can we go? Can we go to our browser? And I don't know. I want to search for C++ move. I'm going to say semantics. What is the meaning of this? And I'd like a little history on that, right? See, what do we find here? What is the origin of move semantics in C++? That's a Stack Overflow. What is move semantics? Well, let's look at this one. He's got 5 upvotes, and there's only 6 there, so maybe that's not so popular. Here's 1682. What is move semantics? I just finished listening to the Software Engineering Radio podcast with Scott Myers. Hero Scott Myers. Anybody? Do we need to have Prince Valiant Scott Myers? Okay. I think we have to take a little sidebar. I know we don't have a lot of time, but Scott Myers, hero pick. Maybe a second. Okay, here we go. This is the guy. So, see, he looks like Prince Valiant. Okay, he's got a whole talk on this, so he gets ribbed by it all the time. So, but yeah, he's a luminary in the field of C++. And if you want to watch this podcast interview, I think that's probably well worth your while. So this was in C++ 10. Most of the new features made sense to me, and I am actually excited about C++ 10 now, but there's an exception. I still don't get moves. What is that? All right, there's 12 answers. The first one's got a lot of upvotes. A lot of people are wondering. I find it easiest to understand move semantics with example code. Let's start with a very simple string class which only has a pointer to a heap allocated block of memory. That's your heap memory, right? So, and you see the keyword new here, right? So, and the algorithm library is included because, I don't know, memcopy. Oh, maybe memcopy is what. Look at that memcopy. What's that? Maybe that's what we should be doing. What's data? Is data an iterator? Yeah, well, data is not exactly an iterator, right? It's an address in memory. Iterator has a little bit of a wrapping around an address in memory. Memcopy, huh? Yeah, I kind of remember. I wonder if we could. Huh? Should we try that? Okay, back from our sidebar into our code. we're going to look at, we couldn't make this work, so what if we were to have instead memcopy? Oh. Oh, but do we need algorithm for that? Is that it? Could be we need algorithm for memcopy. Okay, now we scroll down here to where we had our memcopy. Where was that? Here? Still doesn't like it. Let me double check. Oh, memcopy doesn't have an O in it. Sorry. Oh, yeah. Okay, but it doesn't like that third parameter. What doesn't it like about it? It likes the first two. It says argument of type double is incompatible with a parameter of type size t. Shall we go to definition for memcopy? Oh, well, that's going to take us into some deep stuff, right? So let's get out of it. Help, take me back. Can we go here? Okay. So yeah, memcopy. All right, let's go back to the browser. And see, it doesn't like that third copy because argument of type pointer to double is incompatible. So that's what this is, right? And it's saying that that's incompatible with a parameter of type. So it wants a size parameter there. Okay, so if we go back to our browser, see, what does this memcopy take? Oh, size. Okay. So I don't know. We'd have to look up memcopy. What does memcopy do? C++ memcopy and C++ reference. Or C++.com has something. Copy a block of memory. Copies values of this many bytes from one location pointed to by source directly to a memory block pointed to by destination. Okay, so source and destination. Okay, I think we can handle that. So going back to our code, we're going to do this, right? We're going to say we want to copy a.size things from there to there. Huh? Alright. Okay. So in fact we could make copy be just a little wrapper around that. So where is our let me copy this. Where is our copy function definition? Well, here's the prototype. Can I go to definition here? Okay, so this is doing the sort of member by member copy, right? And what if we were to try to do it in this other way? Oh, arg. Yeah. Huh. Okay. So so now we don't need this because copy is now doing that, right? So let's see if this now will preserve values. No. Here's our output. Same problem, right? The copy is not a good copy. It's got garbage. Garbage, as the French say. All right. Yeah, so it continues to be an issue. I'll try to look into that because it's not resolved in my own mind as to why that's happening that way. All right, so move semantics. Sorry, I got off on a sidebar, as will happen. Um, okay, so, and then let's just get rid of that as well. Okay, so I find it easiest to understand move semantics with an example code. Let's start with a very simple class string which only holds a pointer to a heap allocated block of memory. So class string has a private data element pointer to character, and then it's got a constructor that says size is going to be string length of p plus 1 for the null character terminator, and we're going to allocate size bytes, right? Each character is 1 byte on the heap, and allocate the address of the first of those to data. Then we're going to copy from data to p size. Since we chose to manage the memory ourselves, we need to follow the rule of 3. Oh, there's a rule of 3? Shall we click on what that is? What's the rule of 3? The law of the big 3, or the big 3, the rule of thumb in C++ prior to C++11 that claims that if a class defines any of the following, then it should probably define all 3. Like the destructor, you get a destructor for free, right? Copy constructor, well, you get one of those for free. The assignment operator, well, you get one of those for free. Unless those aren't, the free ones aren't good enough because you have some special needs or whatever. In which case, if you have special needs for any one of these, and you probably have special needs for all 3. Okay, so rule of 3. I'm going to defer writing the assignment operator and only implement the destructor and the copy constructor now. Okay, so the destructor says free up that memory, and the constructor says allocate new memory and copy this to there, right? Or that to here, right? That being the memory that's passed in, right? Which has size. Copy constructor defines what it means to copy string objects. The parameter that binds to all expressions. So that is a variable of type reference to constant string. Binds all expressions of type string, which allows you to make copies in the following examples. So you can copy one string to another. You can copy a concatenation of 2 strings to a 3rd string. Or you can do some function returning a string object and copy that to your string. Now comes the key insight to move semantics. Note that only in the first line where we copy X is this deep copy really necessary. Because we might want to inspect X later and would be surprised if X had changed somehow. Right, so you don't care about X plus Y because that's sort of an object you make on the fly. So you can always get X plus Y again by doing that, but it's a new object, and you're copying that new object which is created on the fly to this object, or some object returned to by a function. Did you notice how he just said X 3 times? 4 times if you count this sentence, and meant the exact same object every time? We call expressions such as X L values. Right? Those are values that get assigned to on the left side of an equation, right? You assign the right side to the left side. So the arguments in lines 2 and 3 are not L values, right? Those are R values. But R values, because the underlying string objects have no names, right? X plus Y is, an object that is sort of created in a fleeting way. It doesn't get a name unto itself. so the client has no way to inspect them later at a later point in time. R values denote temporary objects which are destroyed at the next semicolon, at the end of the next full expression that lexically contains the R value. This is important because during the initialization of B and C, right, these objects, we could do whatever we wanted with the source string, and the client couldn't tell the difference. So C++10 introduces a new mechanism called R-value reference, which, among other things, allows us to detect R-value elements via function overloading. All we have to do is write a constructor with an R-value reference parameter. Inside that constructor, we can do anything we want with the source as long as we leave it in some valid state. So here's a function that takes an this is a ref, double ref. That means you got move semantics. So it's an R value reference to a string. Okay. And string has a member variable called data, which we're going to pass that's data to our data, and we're going to then assign that's data to the null pointer to that's data. And when we return from this function, the fleeting values will be gone and be of no consequence. So we haven't allocated new memory. We've just done a little switcheroo. So he asked the question, what have we done here? Instead of deeply copying the heap data, we have just copied the pointer and then set the original pointer to null to prevent the delete from source objects destructor from releasing our just stolen data. Just stole it, right? Yeah, it's like, yeah, you just stole the data. You didn't make a copy of it, you just took it away. And now it's yours. Right? So there was no deep copy required. In effect, we have stolen the data that originally belonged to the source string. Again, the key insight is that under no circumstances could the client detect that the source had been modified. Since we don't really do a copy here, we call the constructor a move constructor. Its job is to move resources from one object to another instead of copying them. Congratulations, you now understand the basics of move semantics. Let's continue by implementing the assignment operator. If you're unfamiliar with copy and swap idiom, learn it and come back, because it's an awesome C++ idiom related to exception safety. Copy and swap idiom. All right. What is the copy and here we go down the rabbit hole, huh? What can I say? Maybe I'll tell you what. Let me put this link in our discussion, which is here. Okay. And also, I think not this one. Where are we? Oh, there's a this link. Probably could use, I mean, there's one link leads to the other if you follow them, but let's go ahead and put them both in there. Okay. So what is the copy and swap idiom? This is from 9 months ago. What is the idiom and when should it be used? Which problems does it solve? Does the idiom change when C++11 is used? A lot of activity here. Although it's been mentioned in many places, we didn't have any singular what is it question and answer, so here it is. There's a partial list of places where it is previously mentioned. All right. Why do we need the copy and swap idiom? Any class that manages a resource, a wrapper like a smart pointer or an iterator, needs to implement the big three, right? And we saw what that is, right? That's you get these class functions for free, right? The destructor, the default constructor is for free, right? The copy constructor, and I now have four. The destructor, well, I guess yeah. So the default constructor is maybe in a class by itself, but if you need to define the destructor, and that's usually because you've allocated memory on the heap, or oftentimes it's because of that, or if you need to define your own copy constructor or your own assignment operator, then you probably, if you need to do any one, you need to do all three. So while the goals and implementation of the copy constructor and destructor are straightforward, the copy assignment operator is arguably the most nuanced and difficult, as we've seen. How should it be done? What pitfalls need to be avoided? The copy and swap idiom is the solution and elegantly assists the assignment operator in achieving two things: allowing code duplication and providing a strong exception guarantee. Conceptually, it works by using the copy constructor's functionality to create a local copy of the data. Then it takes the copied data with a swap function, the old switcheroo, swapping the old data with the new data. The temporary data then destructs, taking the old data with it. We are left with a copy of the new data. In order to use the copy and swap idiom, we need three things: a working copy constructor, a working destructor, both are the basis of any wrapper, so should be complete anyway, and a swap function. A swap function is a non-throwing function that swaps two objects of a class member for member. We might be tempted to use the standard swap instead of providing our own, but that would be impossible. Standard std swap uses the copy constructor and copy assignment operator within its implementation, and we'd ultimately be trying to define the assignment operator in terms of itself. Oh dear. Not only that, but unqualified calls to swap will use our custom swap operator, skipping over the unnecessary construction and destruction of our class that std swap would entail. Oh dear. Now we're going to get the in-depth explanation. Let's consider the concrete case. We want to manage in an otherwise useless class a dynamic array. Hey, that's what we want to do. We start with a working constructor, copy constructor, and a destructor. Okay, so here we've got this dumb array class, and it's got a dumb array constructor, which uses an initialization list to set its, what do we have for private elements? We've got member size and a pointer to the member array. So we're going to copy this parameter size to member size, and we're going to use the ternary operator here to initialize the member array, and we're going to say, is m size 0? If so, is m size not 0? It's confusing, huh? So this is a Boolean, right? We're thinking of this as a Boolean here, right? So if it's 0, then we're going to say null pointer, right? If it's not 0, that means this is true, and we're going to allocate memory on the heap for m size integers and assign the address of the first of those to this pointer to what? An int, which is m array. So here's the copy constructor. It takes a dumb array, a reference to a constant dumb array, the other one, and just copies size element for element. Well, I mean, yeah. And then uses the ternary operator in the same way that this one did. And there's a comma here? Why is there a comma there? I think maybe that's a typo. I mean, it's a comma separated list, but I don't think there should be. I mean, maybe it parses with a comma there. It's certainly not needed. Okay, so note that this is non-throwing because of the data types being used. More attention to detail with regards to exceptions must be given in a more general case. However, okay. So, here we're using copy. They're putting the stud before the copy? And they have algorithm here. And they're including CSTD def? C standard def? C stud def? Algorithm? I think we were including algorithm. So, yeah, the way copy works is it has sort of an iterator here, which is, I guess in this case, it's just a memory address. So others, memory beginning and end, or one past the end, and the size, right? Oh, no, and where we're going to copy it. So this is the memory location where it gets copied to. It's memcopy that takes a different set of parameters, right? And then we're going to delete marray as part of, this is part of the, sorry, that's the destructor, yeah. Which is sort of the obvious destructor, right? But since you allocated heap memory, you become responsible for doing it. And I don't think a default destructor will do that. I don't know, maybe should we try to see if that works? This class almost manages the array successfully, but it needs the assignment operator overload to work correctly. So here's a failed solution to that. Here's a naive implementation. That doesn't work. And we say we're finished. Well, let's see. Well, what's this doing? So it's saying if we're trying to copy something to itself, then we should just return that thing, right? Why bother? Maybe that's the way. Yeah, see, we didn't do that with our assignment operator, right? We didn't do that check. All right, so that gives me a couple of ideas. One is that, maybe we can use this copy. Do we still have? Yeah, we still have that up here, huh? I mean, where? Here? So, where is the copy? Here, right? Go to definition. All right, sure enough. And so here we're using memcopy. Shall we try? Maybe it's got to be prefixed with std, even though we're okay. So I'm going to say std copy arg.alem arg.alem plus arg.size and alem. I don't see any problems. Maybe it was just the std, which strikes me as a little odd. Okay, and so we do have algorithm here, right? So shall we try it now? Oh, good God! All right, F5. Yeah, no, still garbage. Here it is. But what if we do that other trick, which was so we're going to say if Um, I gotta remember what was the exact thing here. It says, so we're overloading the, yeah. So if we're not trying to copy to itself, then go ahead and do all this. All right. Else just return return this. In fact, I don't think we need the else, right? But it doesn't hurt. Okay. One more try at getting this. Oh, that did the bloody trick. Where's the output? Yeah. So just avoid copying something to itself. I'm not sure why the copy to itself caused the problem, but you just avoid doing that, right? I mean, why would you ever copy something to itself? If you do, fine. It handles it, but it's not needed. All right, well, that seems to be somewhat of an improvement. Back to this example. I don't know. Should we try that? Just to make the example work, just to work through it. So I'm going to exclude this from the project and say add a new item, and that new item is going to be, what was this called? Copy semantics something or other. Copy and swap idiom. Okay, copy and swap idiom. An idiom is like a part of speech, familiar speech, which almost like a quirky thing, right? That just where people use it all the time because it just works, right? All right. So what do we need here? Okay, can I just? So I'm going to copy this into our code. I don't know about the C-stud-def. That's kind of an interesting. I don't know what that is. All right, and yeah, see that comma was a syntax error, huh? Yeah. Yeah, you can't just have a dangling comma there. Here's that copy thing is working fine here. Or it appears to not have any problems. Okay. So I'm going to go back to the browser. So we got this. And here's how a naive implementation might work. Well, let's see. This is the hard part. All right. Let's copy that into our code here. And we're trying to overload the assignment operator. What does it say? Must be a member function. Oh, yeah. I guess we'll have to make it a member function here. This is the destructor. Looks like we're missing something somewhere. So this is the copy constructor. And there's the end of its definition. That looks good. I don't know why the destructor is extra indented here. Okay, now it seems to be all right. And let's just throw in the What does it return? It returns a reference to a dumb array object. Dumb array operator assignment, and it takes a reference to a constant dumb array object, right? Can I just copy and paste this up there? And there's the prototype. So now we have one. So this should be okay now. No? What does it say? Must be a member function. It is a member function. It doesn't like operator here? Definition not found. Well, there's a definition. Hello. Oh, I think I have to be, sorry, yeah, I have to be in the scope of the dumb array class, right? So dumb underscore array, there, okay. This is, remember, this is the naive version, so maybe I should say that here. Naive version. And if this is not equal to other, that's just a typo there, huh? I'm not the only person who makes typos. That's a relief to me. How's everybody doing? We're getting in the last 10 minutes or so here, huh? Okay, so we've got, if we're not trying to assign something to itself, then get rid of the old data. Really? Is that the first thing you do? Don't you want to keep that around? Assign the null pointer to the old data and put in the new. So msize is going to be other.size. Well, other still has its size. Marray is going to be assigned, if msize is more than 0, it's going to be assigned a new block of memory on the heap for msize ints. And then we're going to do copy, which apparently you got to put this little stud in front of the copy. Other.marray, didn't we just delete this? I mean, so maybe that's the problem, right? Otherwise, return this, right? Oh, don't we? Oh, either way, return this, right? So yeah. So I guess, right? I mean, it's kind of, yeah. You're going to end up returning this in either case. If you're not trying to copy it onto itself. But I think it's the order in which case. So let's go back to Stack Overflow and see what's going on there. This now manages an array without leaks. However, it suffers from 3 problems marked sequentially in the code as n. Okay, so the first problem here, second problem there, and third problem here. So the second problem is this delete thing, right? So the first problem, this is the self-assignment test. This check serves 2 purposes. It's an easy way to prevent us from running needless code on self-assignment, and it protects us from subtle bugs, such as deleting the array only to try to then copy it. But in all other cases, it merely serves to slow the program down and act as noise in the code. Self-assignment rarely occurs, so most of the time this check is a waste. It would be better if the operator would work properly without it. Oh, okay. I think maybe I'll put this little comment here. Seems like that's something we ought to have in our code, right? So here's the code. And here's this little number 1 here. So I'm just going to put this down here as saying, yeah, here's the commentary on why that's a problem. Oh, come on. Um, okay. It's a waste. All right. So back to the browser. How are we doing? Oh, we are running out of time. Let's see if we can make this work. Second comment only provides a basic exception guarantee. All right, we're going to talk more about that later. I mean, Wednesday maybe. So if new int of size fails, then the dereferenced object will have been modified, or the object will have been modified. Namely, the size is wrong and the data is gone. For a strong exception guarantee, it would be something akin to this. Okay, so let's go grab that and put it in our growing. So we have I don't know. If I put it down here, then I have the problem of not being in the scope. All right. But now I have a redefinition of this thing, right? Okay, so how are these different, I guess, is the question, right? It's got this check at the beginning, right? Oh, that's the old one, right? So the new one still has this check at the beginning, but we have something called new size, which we didn't have before, right? So we create a copy of the parameters, the parameter being other, right? Create a copy of its size, which we weren't doing before. Then we create a new array first. So we allocate memory for a new array first. And again, we're using the ternary operator to say, are they pointing to the same memory? So is new array, where is new array? Oh, sorry, new array is, this is the assignment operator, and this is the ternary. So is new size empty? If so, just assign it the null pointer, right? If not, that is, if this is of one or more, then allocate memory on the heap. And notice that this is got the parentheses here. Then do the copy and then do the delete. All right, so yeah, we were right that you should wait to do the copy and then assign. So, you know, replace the old data, all are non-throwing. Essentially, we're not doing it catching exceptions, right? And yeah, so that looks much safer. Okay, so should we just comment out this old code here? Copy swap idiom. So I think maybe I'll just delete this, huh? And maybe I should put in the second comment here. Oh, crap. So this is second comment. I'll post this up into the discussion. I know we got to quit here because it's like the last 2 minutes. Namely, the size is wrong and the data is gone. For a strong exception guarantee, it would be need something akin to this, and here it is. Okay. So don't delete the memory until you're sure that you're going to be replacing it, and then you won't throw any exceptions or, you know. The code has expanded, which leads us to the third problem, code duplication. Our assignment operator effectively duplicates all the code we've already written elsewhere, and that's a terrible thing. Okay, we're not done with this. Yeah, this is also a bad version here, right? Oh, and this should be in a comment, huh? Yeah. Code duplication. Our assignment operator effectively duplicates all the code we've already written elsewhere. That's terrible. Okay. All right. So I guess we're going to have to leave this. It is now time. But let's take up here next time. I'm going to go ahead and finish this up and then post it, and maybe make some comments about it in the discussion, which you are free to do too. I am not the only discusser. Although there hasn't been a lot of back and forth there, but feel free to offer some back. Should make like extra points for back and forthing, but you didn't subscribe to this whole model here, so I'm kind of giving you a pass on that. But yeah, next term I guess we're all gonna be on the end of our ropes online. That's a hanging line. Well, we'll see. Okay, any questions about anything before we quit? Like I say, I'll finish this up and post it up, and then I will also post the new project as I finish it. Okay, folks, I know you got other things to do. Nice to see everybody here today. Appreciate your perseverance. Check back with me anytime. Have you graded the bill? No, I mentioned that earlier on. Yeah, you do what you can do, and I appreciate that all that you do, and I will certainly recognize it and give you some feedback for it. It may not be the most timely feedback, but hey, as we wind up this, okay, see you everybody. I'm going to cut it off there.